Okay, so we should see a little red flashing light in the upper left-hand corner of our Zoom window, which indicates that we are recording. And with that, let me turn the floor over to Group 14 to share with us their design.
I thank you, Dr. Traum. Good afternoon, everyone. I'd like to thank you all for attending our presentation. My name is Wojciech Przeputa, and I'd like to introduce my team members, Marcela Abadia, Joao Pedro dos Santos, Ashton Gone, Ollie Goodall, Brendan Modi, Audrey Mayet, and Pelayo Urios. In this following presentation, we are going to demonstrate and break down the subsystems, functions, and achievements of our fully designed compact autonomous microbioreactor, or CAMbox. This device is designed to be capable of cell culturing in fully enclosed vessels under fully automated and controlled conditions through atmospheric gas control, temperature control, shaking of cell cultures, automated liquid transfer, and continuous measuring of optical density and fluorescent intensity. The system will allow for simple yet quick media exchange and consist of easily interchangeable compartments. Our advanced robot gantry system will effectively provide nutrients to the cultures, dispose of collected waste, and maintain a sterilized liquid handling system. In addition, the computer-connected user interface, combined with a series of interior sensors, will allow for continuous scanning of enclosure climate and detailed reports of cell culture conditions. Our emphasis on the compactness of our product's design reflects our hedgehog concept of creating a fully autonomous yet functional microbioreactor with the smallest overall footprint and most efficient use of interior space. Along with this overarching goal, we are able to achieve lower production costs through the greater use of off-the-shelf components and overall fewer materials required in manufacturing. Finally, through its compact design and cost efficiency, the CAMbox is more marketable for a greater scope of consumers, including high schools, universities, and others, which we discuss later on in the presentation as well. So in the following few minutes, my team is going to break down each of the refined subsystems that make up the CAMbox, and we will discuss the unique features that aid in creating the most energy and cost-efficient system. Our subsystems include the enclosure, user interface, liquid handling and ODFI systems, our cooling and heating climate control system, gas control, and our shaker system. Each of these subsystems has gone through extensive analysis and design improvements in order to meet each and every customer need while maintaining this compact structure without sacrificing efficiency and reliability. We will begin this presentation by taking a look at our enclosure subsystem.
For the enclosure, we really tried to go way beyond the customer requirements that were provided. We did this because not only does the enclosure weigh less than 50 pounds and fits within a 500 by 500 by 600 millimeter space, but is also able to maintain consistent internal temperatures through layers of insulated steel. The front panel can also be opened for easy access and internal changes that could be required. The enclosure itself is actually quite complex, so it's best to break it down and start from the outside going in. As you can see in this picture here, the exterior shell is constructed from two bent pieces of A36 sheet steel that are securely bolted to an internal layer of polyurethane foam with an R value equal to 5. The insulation layer is strapped between an exterior and interior layer of sheet metal. It's also important to note that to maintain the desired internal temperatures, any fasteners like rivets or bolts that are used to connect the outside and inside layers will have rubber washers or any other necessary sealants to prevent spillage or leakage of heat. The front door seen here is 350 millimeters by 425 millimeters, which leaves plenty of room for the average user to access the internal components. It's also important to note that the door has a rubber seal around the inside with a latch to tighten the entire door evenly, which is imperative when it comes to resealing the CAMbox and prevents gases from escaping during testing. On the door itself is a window that looks into the well plate to allow the operator to get a visual of what's going on inside of the CAMbox. The window has a shade as well that completely blocks out light and stops any light contamination from occurring during the ODFI scanning process. To prevent the CAMbox from sliding around, on the bottom is our four rubber feet, which prevent any sort of unwanted motion. And while it's not shown here, the wiring in the box is, there's a wiring The wiring is not shown here, but the wiring box is located on the rear, and that's sealed and insulated, so there isn't any concern about wires getting through the shell and potentially losing any gases or heat. To validate the structural integrity of the CAMbox, initial theory using mechanics and material analysis was performed to verify that none of the forces from the gantry would theoretically cause material yielding. So after this, an FEA analysis was done to verify the point of failure, where failure is most likely to occur, which we determined to be the supports on the gantry. And after initial testing was performed and the design was verified to easily support these loads, a worst case scenario was performed where the entire force and moment was placed on a single point on one of the supports from the gantry. And even with a single support, the load did not cause the structure to yield. So we were far within a factor of safety.
So the next subsystem that we're going to present is liquid handling. This subsystem is capable of providing nutrients and media to the cell culture, and it allows incubation periods of 2 weeks through its ability to sequester and neutralize its own waste. It's also able to sterilize itself throughout the process. The biggest considerations when designing this system were the flow rate and volume accuracy. The flow rate had to be between 225 and 300 microliters, and the volume accuracy had to be 0.1 microliters. So these needs were the determining factor for choosing a motor. Calculations will be shown in a later slide to show that our device does meet these requirements. Additionally, we opted to use disposable tips to make sure that no cross-contamination would occur during the process. So the system uses a NEMA 17 stepper motor, a lead screw, a 20 milliliter syringe with a rubber stopper, a 3D printed plunger, and universal disposable pipette tips. The lead screw and the plunger are held in place through a bracket, which is what enables the plunger to move up and down as the motor rotates the lead screw. The plunger is held in place by a dowel pin, and the reason the plunger was 3D printed was to achieve the shape it needed to fit with the bracket. The system also includes 5 containers. The container in the front is for placing the pipette tip racks. This container was made with the purpose of making sure that the pipette tips can be placed into the enclosure without compromising their sterilization. Additionally, there's a container that holds the liquid that's going to be added to the well plates or the falcon tubes, one that holds the waste and one that contains sanitizing fluid. The container on the far left is where the used pipette tips will be disposed of. This container is also going to serve as a mechanism to remove the used pipette tips off the syringe. So to do this, the pipette will lower into the opening, positioning itself so that the top edge of the tip will be in contact with the bottom surface of the container opening. Then as the syringe moves upwards, the pipette tip will be stuck on the container edge and be pulled off. These 5 containers are placed in a custom-made sheet metal holder that is screwed into the floor of the enclosure. This was done to avoid the containers moving or falling over if the device were to be moved. We decided to use this holder instead of fixing all the containers to the enclosure floor so that the user could easily remove individual containers when more liquid needs to be added or waste needs to be removed. It's also important for us to note that even though using a multiple pipette system would have given us a faster process time, we chose to go with a single pipette because it would reduce complexity since multiple well plate sizes and falcon tubes need to be accommodated for, and because it went along with our overall purpose of keeping the device compact. If we chose multiple pipette lengths, there would be a greater length for the gantry to have to go through in our enclosure, and it would have brought our cost up. So the flow rate of the system was calculated using the linear velocity and cross-sectional area of the outlet. It was determined to be 311 microliters per second. So this is above the customer need flow rate of 300 microliters per second because it uses the maximum motor RPM. And taking into account that the motor won't always be functioning at maximum speed, this flow rate is going to be lower. Next, the dispense accuracy was calculated as 0.6 microliters by using the motor step angle accuracy. This was also higher than the accuracy the customer need said, which was 0.1 microliters. We were also able to confirm that no aerosols would be created by calculating Reynolds number, since the result was 2,300. Lastly, the time it will take to fill up a 384 well plate is a little over 2 minutes, and this calculation takes into account liquid dispensing and gantry motion. Through the calculations shown on this slide and the system features, our system is able to meet all customer needs.
The next subsystem we're going to talk about is the user interface. So the user interface meets all customer needs related to it, where all functions can be safely stopped at the same time. It has an intuitive interface with visual indicators and is programmable. As can be seen in this slide, the user interface is composed of a computer, an Arduino board, sensors, an LCD screen, and an emergency button. Sensors located inside the control box allow the collection of data that is generated by the Arduino board. The time of the experiment, the gas or gases that are being added, and the temperature inside the device are some examples of data that is being collected. The laboratory computer needs to be connected to the device to allow the user to control the different parameters applied to the cell cultures. The LCD screen allows the user to see what parameters are being applied to the current experiment. And the emergency button allows the device to safely stop all functions at the same time. Both the screen and the emergency button are located on the right side of the enclosure. The goal is to design an intuitive and programmable system to facilitate the visualization of the parameters that are being applied to the device and to make it as simple as possible to be more cost-effective, reflecting our headshot concept.
So next, we're going to go ahead and talk about the climate control subsystem. Being able to control the temperature of these cell cultures is an important independent variable in a lot of the biological experiments that the customer wanted to run. So we had 7 specific customer needs associated with the climate control system. Of these, the 2 most important ones were the temperature range, which needed to be from 4 to 70 degrees Celsius, which is about 40 to 160 Fahrenheit, which is really a wide range of temperatures. You're talking about something from as low as like the inside of a refrigerator up to about the temperature of a cup of coffee. And then the other one of these that's very important is the 15 minutes to reach set point requirement. So when you combine these 2 capabilities in a single device, it's really not like anything else you can get out there. And yeah, so one other thing I'd like to touch on before we go to the next slide is that the main reason for, I'm sorry, I was reading that. So yeah, we used 2 separate units for heating and cooling. The main reason was because the cooling unit couldn't reach the high temperature that we wanted. But an additional advantage of using a separate heating unit is that the heating unit can also function as a defogger during cooling. So this is the specific model we use for our cooler. It's a Seifert 315-2303 thermoelectric cooler, and it uses the Peltier principle for cooling rather than something like vapor compression, which is more common in refrigeration. And there are some important advantages to using thermoelectric compared to vapor compression, especially with our device and our goal to make it as compact as possible. Thermoelectric coolers are much more compact than similarly powered vapor compression coolers. They last longer because they don't have any moving parts. And another thing that isn't listed here, but thermoelectric coolers are also safer and more environmentally friendly because they don't have any refrigerants, and a lot of the refrigerants being used today in vapor compression cycles are considered damaging to the ozone layer and a major contributor to greenhouse gas emissions. And okay. So this slide shows one of the more important results in the heating and cooling analysis, and this is the time to reach set point as it relates to the fan speed. So our system uses forced convection, and we have a variable speed fan to facilitate that. So this graph shows that as you vary the fan speed, the time it takes to reach the set point changes. So for our fan, we had about 7.48 meters per second, which would be on the x-axis, which gives the time to reach the set point of a little under 12 minutes in this case. So one other thing to point out, this graph only represents cooling of a 50 milliliter conical tube. So we also have separate graphs for well plates and for heating. So here's the fan we used for forced convection. It's a variable speed fan from the brand Supermicro. It has a volumetric throughput of 25.2 cubic feet per minute and an outlet of 1.57 inches by 1.57 inches. And you can see on the right the calculations to determine the air output speed based on the volumetric flow rate in the outlet area. And this is ultimately going to be important to determine the convective heat transfer coefficient and the time required to reach the set point. So this is our heating unit we selected. It's a 200 watt DVK FGC 3000 fan heater. Has a maximum temperature of 70 Celsius, which is perfect for our requirement. Has a 300,000 hour lifetime, which is about 30 years. Uses a PTC heating element, which is like a resistance type of heating, but it's more efficient and safer because it's self-regulating. And yeah, it also functions as a defogger, as I previously mentioned. So here's the same graph that was on one of the previous slides, except for heating of a conical tube. You might not be able to tell from this, but these times are slightly slower because we're reaching a higher temperature with heating than a lower with cooling, basically. So it can get from 20 Celsius to 70 Celsius in just under 14 minutes. And then on the right here, we have a diagram showing the way we modeled this process, and it's the cylinder and cross flow under forced convection, which is based on the fundamentals of heat and mass transfer process in the book by, I believe, Bergman. So here's some of the analysis and the detailed math required to determine the time required to reach the set point. So it's mainly based on this thermal circuit and the cylinder and cross flow, as I mentioned earlier. And there's a separate analysis that isn't here, but it was for the well plates, and that's based on parallel flow over a flat surface. So these calculations are basically just to determine the heat transfer rate into the cultures through the air in the enclosure, through the container, and then through the culture itself. And you can see for a fan speed of 7.48 meters per second, which was the speed our fan was capable of achieving, we have this Reynolds number and this Nusselt number and this convective heat transfer coefficient based on the Zukakis correlation. And finally, we have the heat transfer rate. And one other thing that isn't here is the heat load, which is used in this final equation on the bottom right. So the heat load is just based on the Q equals MC delta T equation, which is just the mass and the specific heat and the temperature differential of the things being heated. And you divide the two, and then you have the time required to reach the set point.
So the next subsystem is gas control. The three customer needs that the gas control should meet are operational lifetime of at least 10 years, be able of injecting 5 different gases, and incubation periods of at least 2 weeks. As well as the rest of the bioreactor, the gas control also follows closely the hedgehog concept. So it is located outside the bioreactor to save space inside of the enclosure. Basically, the system consists of gas inputs and outputs, solenoid valves, and binding tubes that connect the whole system. With this system, the bioreactor is capable of injecting and regulating the 5 gases customers specified, which were nitrogen, oxygen, hydrogen, carbon dioxide, and methane. And this is done by attaching external tanks to the reactor. The amount of gas is controlled by the solenoid valves, which allow the user to control the composition of the gases, and therefore control the atmosphere of the cultures. For safety issues, the bioreactor also comes with a rooftop vent connected to the fume hood. That in case of emergency, it will evacuate all the gases inside the chamber. Also, the exhaust is sealed with a lid to keep all the atmosphere inside. With all the material equipped in the gas system, the reactor is capable of incubating periods longer than 2 weeks, which will be enough to reach the 1,000 E. coli generations. And according to the manufacturer ASCO, the valves installed should have an operational lifetime of around 5 to 20 million cycles under normal workload, which should meet the customer need without any problem.
Okay, so I'm going to talk about the ODFI subsystem for the product. The main function of the system is to record optical density and fluorescence intensity. So the customer needs map shows all the customer needs that apply to the subsystem, in which the design does meet all these needs. And of all the needs it meets, the two most important are to be able to measure optical density and fluorescence intensity of the wells and conical tube samples. These are the most important needs, as without this, not only is the subsystem useless, but so is the entire product. Therefore, the ODFI subsystem does not only meet these needs, but it is designed to do so in a way that synergizes with most of the other subsystems in a very unique manner. So here's the ODFI reader itself. The reader contains mostly OTS parts where the components are already used in other products in a similar fashion, demonstrating a technology readiness level of 7. The ODFI OTS parts include a PMT detector, filter cube chassis, excitation and emission filter glass, dichroic mirror, standard mirror, and a xenon lamp. All of these are already in use with separate commercial plate readers, although compared to commercial products, the CAMbox is able to give OD and FI readings during sample incubation. Also, the system shown is designed to work along with the liquid handling subsystem, where they both operate on the same gantry arm, and this will heavily reduce analysis times during operation and simplify the user interface programming. So the speed to evaluate the vitals of all the samples in the largest well plate size is governed by the light flash of the reader and gantry motor speed. The ODFI reader is approximately 607 grams, which is around 1 pound. Therefore, there's an 80% load onto the motor, also accounting for the liquid handling mass. And by using the governing equation to determine the time it takes for the gantry to move the reader across the well plate, it will take around a minute to analyze a 384 well plate. It is important to note that this system is uniquely designed to read both OD and FI at the same time. Therefore, the FI and OD canal shown in the picture by the light green and red arrow, respectively, are separated by two 384 well plate diameters. This design feature adds to the total area coverage by the gantry, but greatly reduces the total analysis speeds. One of the customer needs was to be under a $10,000 budget, and upon initial inspection, the ODFI subsystem is able to take the entire budget if it was designed in that way. Therefore, it is important to note that the cost breakdown of the system, where the entire ODFI reader system is around $1,500 for OTS parts, $50 for materials, and $60 in manufacturing. Also, the reader is 3D printed using ABS plastic. And if you look closely at the picture on the left, the chassis itself has a lot of empty space. This chassis was designed like this in order to reduce the amount of material required for the reader. And by using 3D printing and reducing the total amount of material printed, a lot of the cost for the system is conserved. So for one of the major customer needs of OD measurement capability, absorbance within the cell culture will be monitored at a 600 wavelength level to ensure non-lethal dosage. And by looking at the picture on the left, the green arrow represents the light path of the absorbance from the cells, which are excited from an LED panel under the well plate. And the light is then reflected at a 45-degree angle from the mirror on the top left. And also by using this 600 wavelength level, this will synergize with the FI reader, which will be talked about next. And the synergy will reduce the number of different filters, lights, overall parts needed, relating back to the hedgehog concept of being as small as possible. So for the other major customer need of FI capability, fluorescence will be measured by the excitation and emission of Texas red fluorescence. This will ensure a red range of around 560 to 640 nanometers. And once again, this synergizes with the OD reader by utilizing a similar wavelength range. And by looking at the picture on the left, the xenon lamp will shine and reflect down on the sample from the emission filter and the dichroic mirror. And then the fluorescence, when excited, will travel back up, filtered through the excitation filter, and then passing through the dichroic mirror, hitting the PMT detector. So both the OD and FI reader operate on the same PMT detector, which will reduce the parts and space required, once again, going back to that hedgehog concept. So another customer need also requires the white light illumination of the samples, and our system is designed to use an OTS LED panel that will be a part of the shaker system. The LED panel will operate in the red range of around 600 to 660 nanometers to ensure non-lethal wavelength dosage. And this LED panel synergizes with both the OD reader by sharing the same LED panel and the shaker subsystem by integrating itself under the well plate inside the shaker, which we'll talk about more in detail a little bit later on. So overall, as mentioned, throughout the specific details of the system, by working in that red range of around 600 nanometers with lower intensities, all the cell samples will not be frozen or die from the light dosage, meeting that customer need of not having any lethal dosage hit the samples. So a couple quick notes about the life expectancy and the functionality. The parts that feature a life expectancy are the PMT detector, xenon light, and LED lights. And the LED lights are expected to have a lifetime of around 50,000 hours, which is about a 5.7-year lifetime, although this part is very inexpensive and easy to replace. And the PMT detector and xenon light have a lifetime of around 500,000 hours, which is well over that 10-year need. As for functionality, the reader is easy to assemble, which allows for the replacement of different filters if specific cell samples want to be observed. Also, the PMT detector, xenon light, and LED panel can be separately programmed. The ODFI reader's movement is housed on the same arm as the liquid handling, as mentioned before, which allows for the easier programming too.
I will now be going over the shaker subsystem. So shakers are important for this application since they aid in mixing and aerating cell cultures. The shaker is required to meet 5 customer needs, but the main 2 that we aimed to incorporate into the subsystem were to shake the cell cultures in linear orbital, double orbital motions, and to ensure that the various well plates and tubes are accommodated for. And in this design, all customer needs were met. So to the right, we see the isometric view of the shaker. The shaker moves by having motion transmitted from a DC motor and a NEMA motor. The motors will help to move the shakers linearly with the help of springs, camshafts, and a railing system. And the combination of these 2 motors will work to create the orbital and double orbital motions. And as we see here on top of the shaker, that's where the well plates and the well tubes will actually sit. This is a metallized surface that we can change out and it'll hold and accommodate for all the different sizes. And the shaker itself will be bolted down into the enclosure, but due to its small size, it'll be accessible for any user. So it goes back into our hedgehog concept of compactness. Some things to note about our shaker is that the maximum velocity was found to be 14.49 meters per second. And as mentioned, the well plates and tubes are interchangeable due to the magnetized trays that they are placed on. So this feature does make it much easier for someone to switch between the tubes and the trays and the plates. In addition to this, the trays will house cultures. The trays that will be housing the cultures are made of aluminum, which meets the customer needs of ensuring that the cells do not make contact with non-porous material in the case of overspill. So we'll go a bit more into overspill later on. And in addition to meeting this customer needs, we found that manufacturing this piece with aluminum worked well because of its magnetic properties, and it works with magnetization. So the images here show the shaker without the platform that will hold the well plates and tubes. So on the left, we see that at the bottom portion of the image, there's the compact round DC motor, and this will provide linear motion to the system with use of springs and camshafts. And above it is this platform which will hold the interchangeable attachment, and this will also move linearly with the NEMA 8 motor in a similar fashion. And to the right of this is an exploded view of the actual platform itself, and it shows how it slides onto the railing system. So we see the spring as well as the part that holds the attachment. So the springs help to bring back the shaker subsystem to the point of origin. And it's also important to note that in this bioreactor, the shakers can only hold one well plate or a group of tubes at a time, which goes back again to our hedgehog concept of compactness and also using space efficiently. So this slide here, it shows the top portion of the system along with the interchangeable attachment that accommodates for the tubes and plates. So the image on the left, it depicts a well plate seated into the attachment. And as we know, it's magnetized, and within that attachment, under it is what will hold an LED box. So this works in synergy with the ODFI system, and this will help the LED illuminate white light into the cell cultures. So a challenge that we faced in creating this design was deciding if we would require a lid or not. So this is the main concern because we wanted to avoid overspill and cross-contamination of the cultures. So to determine if a lid is necessary, we conducted a fluid analysis, as you can see here, to determine the maximum acceleration that would be needed to cause overspill of the cells. So to the right, there's two images of a design of a 96 well plate from its side view. So this comes specifically from a manufacturer called BioOne, who makes a bunch of lab equipment. And the top right image, it depicts the cell, it shows the cells inside the well plates. And the one below it depicts it when it's on the threshold of spilling. So we decided that for this analysis, we were going to use this specific well plate because it satisfies one of the customer needs. And in addition to this, it was the smallest in depth. So thus it would have the highest chance of overspill. And with this in mind as well, we didn't see the necessity of performing an analysis on the 96 deep well plate nor the conical tubes, since they are larger in depth. So in research, we also found that for our applications, generally the wells are filled about 1/3 of the way in an experiment. So to ensure that spillage won't occur, we conducted this analysis with the assumption that the wells were filled 40% of the way. So through this analysis, we found that the maximum acceleration that the cells can withstand before overspill would be 18.745 meters per second square. And we also found the maximum acceleration for the shakers in the different motions. So for linear motion, the maximum acceleration that the shaker would reach would be 13.69 meters per second squared. And for both the orbital and double orbital motion is 17.47 meters per second squared. And so since both of these values are less than the acceleration in which the cells would overspill, this mitigates our concern in that the shakers would overspill and would cause cross-contamination. So thus we decided that a lid would not be necessary in our design. So this is a very important finding for us since we did not need to create another mechanism to put on or take off the lid. And this directly relates back to our hedgehog concept of creating a compact design, and it also simplified this subsystem for us.
So here we're going to discuss the technology readiness level of each subsystem based on the description of the level seen in the table. So starting off with the enclosure, most of the parts on the enclosure are custom made and will be manufactured by us. Since the calculations have been done, but it's not made or tested yet, it has a technology readiness level of 3. Next is liquid handling, which received a technology readiness level of 3 because even though most of its components are OTS and we did calculations for it, testing hasn't been done in the relevant environment. The user interface uses all OTS components that are fully developed versions and function as we need them to for our environment, which makes it a level 7 in technology readiness. Now, in the case of climate control, we're using OTS components that are fully developed and ready to be implemented in an environment like ours, which is why we gave it technology readiness of level 7 as well. For our gas control system, even though some parts are custom made, the main components are the solenoid valves and the vinyl tubes, which are both fully developed and functional for our purposes, so it also receives a level of 7. As stated before, the ODFI's components are already used in other products for similar functions, so they also have a technology readiness level of 7. And lastly, the shaker subsystem has a technology readiness level of 3 because the calculations were done, but the components aren't developed and haven't been tested for our purposes. Now we're going to look at the cost of the CAMbox. So the table shows the individual cost of each subsystem, taking into account OTS parts, modified OTS parts, raw materials, manufacturing labor, assembly labor, and energy consumption. So from the pie chart, it can be seen that most of our cost comes from OTS parts. By choosing to create a compact design, we were able to use more OTS parts because smaller parts worked for our design. So this was especially the case when looking at the gantry and climate control system. By having a smaller footprint, we were able to purchase one of the smallest gantries made by this company, so the cost didn't make us exceed our budget, and we won't be spending any time manufacturing or assembling. For the climate control, since we have less space that needs to be cooled and heated, we were able to buy a smaller heater and cooling unit. And although most of our cost goes to OTS part, we're still well below the $10,000 budget. And using OTS parts ensures a higher accuracy and will save us a lot of time manufacturing and assembling the overall CAMbox.
We believe that the CAMbox should be selected for prototyping due to its mass market appeal, low weight, and overall compactness. It sits in a unique position as it meets all requirements while costing significantly less than the allotted budget. The CAMbox has the potential to not only be bought by large universities, but also by high schools and smaller research or educational facilities that would normally be turned away by a larger price point and a more industrial sized piece of machinery. The CAMbox provides groups of people with even a moderate interest in cell culturing and development an opportunity to interact, understand, and test with various gas combinations, temperature settings, well plate configurations, and shaker patterns. It is our belief that the CAMbox achieves all of this without sacrificing quality, but while optimizing cost and spatial efficiency, making it an ideal candidate for selection. In conclusion, the Compact Autonomous Microbioreactor, or CAMbox, meets all of the given requirements while maintaining true to our goal of creating a microbioreactor that is both small and cost-effective. We believe that the CAMbox has the potential to put autonomous cell culturing not just in the hands of advanced research labs, but into the hands of students, teachers, and a wide market of other interested researchers. From all of us on the CAMbox team, I would personally like to thank you all for attending and listening to our presentation today of the Compact Autonomous Microbioreactor. We will now turn it over to you guys for any questions that you might have, and thank you for listening.
Okay, excellent. So I didn't need to stop you guys. You've actually got 6.5 minutes to spare. So good job with the timing. And just for the sake of the recording, because the comments in the chat don't get recorded, but I just dropped a comment in here that I really appreciate the idea of high school teachers being able to use the design. I think you guys with your headshot concept were unique among all the groups. In that yours was small, compact, and simple enough that we might imagine it being used not just in a research environment, but also in a teaching environment. My wife is a high school chemistry and biology teacher, and so I've got a sort of special place in my heart for equipment like this that can potentially be used for teaching in addition to research. So appreciate that you guys thought about that. Anyway, let's jump into the panel. Looks like Tom has a question.
Yeah, could you flip back to the FEM slide, please?
Sorry, which slide did you say?
The finite element analysis slide back. I believe you're talking about the gantry system. It's way back towards the beginning, I think.
Yeah. Slide 6.
Right here.
No, 6.
It's the gantry one.
No, go back.
Ah, I see.
Yeah.
There it was. There it was. That looks like solid elements on that FEM. Is that correct?
Yes. Yes. Yes, it is.
Don't do that. That's a thin structure. That's plates. That's if you're going to do a FEM, which you shouldn't be doing a FEM to begin with. If you're going to do a FEM of a thin plate structure, use plate elements. I could talk for hours about things that people do wrong with FEMs, but I mean that's just like big red flag to me. It looks from the renderings that you've got that you've got some sort of coating. You said this was a steel box. Is it like painted or is it intended to be bare steel? What's going on with that?
Can you hear me?
Yeah.
Oh, okay. Sorry. I think the idea was that there would be a coating around it just for general, just around the exterior. But I think that my idea might have been shelved after we realized that we could put feet on the bottom of it to help with grip. Because originally the idea was going to put a coating around the entire thing, so it wouldn't slide around. But we ended up going with a feet option, a rubber foot option.
All right. What's going to happen to potentially bare steel if people are putting hot, wet environments in there? People are using things like bleach to wipe things down.
I mean, theoretically, it could corrode. Is that what you're getting at? I'm assuming.
Yeah.
Yeah.
All right, so
sorry, go ahead.
Oh, just something to consider. You go ahead.
Well, I know our device specifically doesn't use bleach, so that wasn't exactly a concern when it comes to corrosion. But
Well, you may not have bleach in the device, but somebody's going to go in there and clean it.
In that case, I guess we'd recommend after just proper maintaining, cleaning the inside with a material that doesn't promote corrosion. I guess that would be something that we'd have to specify.
Okay. Let's see. You have motors on your shaker system that had RPMs of like 11,000 and 14,000 RPMs.
Yes.
Like what? That's eyebrow raising. What are those motors doing, and why are they moving so fast?
They're variable motors, so they're able to be adjusted to whatever frequencies are required.
Are frequencies on the order of like 200 hertz required?
Well, I mean, depends on what the user wants, really. I think we were going for a customizable device that if someone wanted, for whatever reason, to shake something that aggressively or in that sort of pattern, I guess we could accommodate for that. But I mean, it was more of a have room for safety in case someone wanted to do that specifically during testing.
Are those sliders just held against the cam on the motor by springs?
Yes, they are.
Are the springs going to be able to react quick enough if that thing's spinning at 14,000 RPM?
I mean, I wouldn't be able to answer that correctly without more further research into that.
I think that that is way overkill on your shaking frequency. The other thing I'll note there is you've got on the slide you've got velocity of your shaking mechanism, right? So it's moving at 14.5 meters per second. Why does velocity matter when you're shaking something?
Audrey, I don't know if you could speak to this better.
Well, I suppose that the velocity matters in it, just so to see at how fast it would be moving and it's in how quick those the shaking mechanisms would occur. Because initially we had the angular velocity, but also since it is moving linearly, we wanted to find the velocity of it as well.
Well, if I'm shaking something, I'm generally going to be curious about what the acceleration is. And then a few different teams have done something like this, and I'm not a fluid slosh guy by any means, and I'm sure that PhD theses have been written on this sort of thing. But it seems like if you're talking about a sort of, repeating shaking of a fluid, you're going to be interested in more than just a single velocity and where that the inertia of the fluid is going to how that's going to, I don't even have the terminology to slosh the fluid in one direction for a single acceleration. It seems like it's a much more complicated problem than that. I know, just from my experience of walking with a cup of water from the kitchen to the table, right? Like I have all sorts of sloshing issues to consider, right? So I think it's maybe more complicated than what most of the teams are taking a look at here when you talk about like resonance of your your fluid moving back and forth. See, I've got some other stuff, but I recognize that other folks might have some questions. So.
No, that's good feedback. And there was some analysis on the acceleration as I'm showing on the slide right now, but there's definitely a lot more to look into. Like you said, the shaker system is a lot more complex than most of the other systems.
Okay, do we have questions from other panelists?
I'll keep going. So I do want to, I'll give you guys credit when you're talking about your heating and cooling system. You guys were the only ones I think that I've seen so far who have mentioned environmental concerns. And I certainly appreciate that. It was Earth Day yesterday, and actually on our grading rubric, we've got a slot for considering economic and environmental and societal factors. So I definitely appreciate you guys, kind of keeping that in mind. I know that's maybe not the primary driver, but that is a good aspect of your system there. For your heating system, you'd mentioned that you've got a heating fan. I think maybe on the next slide or two. Yeah, there it was. And you said you've got a maximum temperature of your heating. Is that the maximum temperature of the air that your fan is outputting is 70 Celsius?
Yeah.
What's your customer's requirement for what they want inside of their chamber?
Well, their requirement isn't for the air in the chamber, it's for the cultures, but that was also
Okay.
70 Celsius.
Okay. So how are you going to get cultures to 70 degrees Celsius and in what kind of time if your fan is just putting out 70 Celsius?
Well, so their requirements, they only wanted it within like 2.5 degrees Celsius. So it's not probably, obviously it can't get quite to 70 Celsius, but it'll get infinitely close as time goes on. So it will get within 2.5 Celsius in under 15 minutes based on the forced convection analysis.
Okay, because you've got a Peltier plate in there too that you can change the direction of the current flow and use that to heat as well, right?
Right.
Does that have enough capacity to get you to 70 degrees Celsius, or can you use that in combination with the fan?
No, the maximum operating temperature of that is 60 Celsius, I think. They could be used in conjunction, but it will not get it all the way to 70 Celsius.
So I'm not super familiar with Peltier plates. Are you saying that if the temperature on the hot side is above 60 degrees, that it just won't put out any more heat?
I think it's based mostly on the electronics inside of it, that it won't get over 70 or 60 Celsius.
what's going to happen when the fan cooks the interior of the system to 70 Celsius or 69.999 Celsius.
What do you mean by that?
I mean, if the Peltier electronics are going to fail, above 60, or maybe they won't fail, maybe they'll just shut down.
Okay, I understand your question. It's not that they're going to fail, it's that they aren't capable of outputting that much heat based on the amount of electricity going through the system, or that temperature.
So if the hot side is at 69 degrees or 61 degrees, and you run a current through there, it's not going to get any hotter. Again, I'm not
well, it can only run so much current based on 100. So that's the one run from a standard 120 volt, 20 amp outlet.
Mm-hmm.
So if I could just jump in real quick with a maybe point of information on Peltiers, that temperature is usually the temperature. They're solid state refrigerators, so there are no internal electronics. It's just ceramic in there, but that temperature is usually the temperature at which the solder joints start melting. So if you run them up hotter than that temperature, there's a potential for internal damage.
Okay. Yeah, I wasn't aware of that. The solders could fail on that.
All right, and maybe in the last couple of minutes, I got one more if nobody else wants to jump in.
Nope. Looks like the last question's for us.
On the fluid handling system, you've got a Z-axis that is driving the plunger mechanism.
Yeah, it's the NEMA motor.
Okay, and that's out of line, right? So you're gonna tend to rack the plunger within the syringe and react that moment with the basically by the whatever moment you can create on the between the syringe and the plunger tip. Is that going to cause you any problems?
We haven't done the calculations for that, but I don't think it will. We'll definitely do the calculations for it for the FDR, because I hadn't thought of that in that way.
Okay. All right, and maybe that was quick. So one more. You've got a dispensing accuracy, and I haven't asked anybody else this either, but you've got a dispensing accuracy that seems like it's based on just the stepper motor's precision. Is that the only source of variation in the system?
I think so, yes. I know that the lead screw has an accuracy as well. I didn't take that into consideration because it was small, if I'm not wrong, but yeah, I only took the stepper motor accuracy into consideration for this one.
How about the rigidity of everything else in the system? Does that contribute to it at all?
I don't think so. The pipette itself shouldn't be moving because it's connected to that bracket on the actual gantry, and the only other thing that would move is the pipette, like the entire system going up and down, which the gantry moves.
Okay.
All right. So we are at 1:30, which is the end of time. So let's wrap it up there. This was group 14, right? Thank group 14 for presentation. Let me stop recording.